Hey everyone, so today I'm going to be reviewing variation of parameters, and this example is from Dawkins, section 3-10. So our problem is to find the general solution to the differential equation, which is y double prime minus 2y prime plus y equals e to the t over t squared plus 1. So this happens to be our homogeneous differential equation, and from here we need to find the characteristic polynomial, which is m squared minus 2m plus 1 equals 0. So this is a perfect square trinomial. So we have m minus 1 squared equals 0. And from there, our m1 equals our m2, which is 1. So now we have our yc, y1, and y2. So our y of c is c1 e to the t plus c2 t e to the t. So now after this, we can solve for w using our Wronskian, which is y1 and y2, and then y1 prime and y2 prime. So our y1 is e to the t, and our y1 prime is e to the t as well. y2, te to the t, and the derivative of y2 is e to the t plus te to the t. So now we can solve this, and it's y1 times y2 prime minus y2 times y1 prime, which gives us e to the t times e to the t plus te to the t minus e to the t times te to the t. So after solving, we get our w to equal e to the 2t. So now we can solve for our w1 and our w2. w1 is 0 and f of x, and y2 and y prime of 2. So we have 0 over e to the t over t squared plus 1, which is our f of x from up here. And we have te to the t over e to the t plus t to the t. So now solving for this, we get 0 minus te to the t times our f of x, which is e to the t over t squared plus 1, which simplifies to negative te to the 2t over t squared plus 1. So that's our w1. So now our w2 is the same but flipped, so we have y1 and y1 prime and 0 and f of x. So it's the same process, e to the t and e to the t, with 0 and e to the t over t squared plus 1. Solving, we get e to the t times e to the t over t squared plus 1 minus 0, which leaves us with e to the 2t over t squared plus 1. So now that we have our w1 and w2, we can start solving for our u1 prime and u2 prime. So u1 prime is w1 over w. And from up here, our w1 is negative te to the 2t over t squared plus 1 divided by e to the 2t. Simplified, that is negative t over t squared plus 1. u2 prime is w2 over w, which equals e to the 2t over t squared plus 1 divided by e to the 2t. After simplifying, we are left with 1 over t squared plus 1. So now we can solve for our u1 and our u2. So u1 is just the integral of u prime 1 dt. So taking the integral of negative t over t squared plus 1, using u sub, we are eventually left with negative 1/2 times the natural log, the absolute value of t squared plus 1 plus c1. And for u prime of 2, the integral of u prime 2 dt, it is the integral of 1 over t squared plus 1 dt. So this is actually an integral with inverse trig. So the integral of 1 over t squared plus 1 is the arctangent of t plus c2. So after this, we are real close to finding our general solution. So we need our y of p, which is u1 times y1 plus u2 times y2. After plugging in and simplifying for what we need, we are left with a y of p equals negative 1/2 e to the t times the natural log of t squared plus 1 plus t times e to the t arctangent of t. So now we have everything we need to solve for the general solution, and the general solution is y equals yc plus y of p. So after plugging in y of c that we got at the very beginning and the y of p that we just solved for, our general solution to this differential equation is y equals c1 times e to the t plus c2 times te to the t minus 1/2 e to the t natural log of t squared plus 1 plus t times e to the t arctan of t.